Hello students and welcome to the course Urban Transit Tracks, Stations and Yards. Through our previous lesson, we learned that rails and sleepers are connected and fastened together using fasteners. Dog spikes, round bolts, and fan bolts are primarily early techniques widely used in the railway system. However, dog spikes tend to loosen over time due to vibrations and temperature fluctuations, requiring frequent maintenance and tightening. Round bolts and fan bolts are also susceptible to loosening and may lead to the track misalignment, increasing maintenance demands. In this lesson, we'll learn about some improved fastening systems and parts. In response to issues caused by drawbacks of the dog spikes, round bolts, and fan bolts, the development of the sleeper screws emerged as a more reliable solution. Sleeper screws are threaded fasteners that can be easily and securely screwed into the sleeper. This design prevents loosening and provides a stable connection between the rail track and the sleeper. By addressing the drawbacks of the dog spikes and fan bolts, sleeper screws have become a standard in modern railway construction, ensuring safer, more efficient, and less maintenance-intensive rail system. Screws with diameter of 20 mm are called plate screws and are used in place of round spikes for fixing rails to sleepers with the help of anti-clip bearing plates, while screw spikes with a diameter of 22 mm are called rail screws and are used to directly fasten the rail to the sleepers with or without the use of bearing plates. Sleeper screws are used in the rail fastening systems for fixing either the rail base plate to mainly the wooden sleepers or bearers, or for fixing the elastic clip to tension clamp to the concrete sleeper. In Central Europe, the sleeper screw types SS of the German railways are widespread. In the early days, dog spikes and sleeper screws are used to fasten rails to wooden sleepers without any other fittings, but in this case, they are generally less effective. Base plates offer better load distribution, stability, and alignment control, leading to safer and more durable tracks that can handle the demands of the modern rail transportation. Rail base plates, typically made of steel, are flat metal plates designed to hold the rails securely to the sleepers. They offer a larger contact area between the rail and the sleeper, distributing the load more evenly. Base plates are provided with sloping upper surfaces and upright ribs between which rail is locked. Bolts, clips, and other advanced fastening mechanisms are used to attach the rails to the base plates. This method enhances track stability, allows for better alignment control, and reduces the risk of rail movement and wear. The use of base plates has become more common in modern rail infrastructure due to their improved performance, reduced maintenance requirements, and ability to handle the demands of high-speed trains and heavy loads. As rail technology continues to evolve, base plates and other advanced fastening systems play a crucial role in maintaining safe and efficient railway tracks around the world. Using base plates has the following advantages. The vertical load is distributed over the large area of the sleeper. This lengthens the service life of the sleeper. The horizontal load is absorbed better because of friction and because it is distributed all over the fastening anchored in the sleeper. Base plates are excellent for sustaining large lateral forces if large cant deficiencies are provided. The overturning moment causes less force on the fastenings in the sleeper. Base plates have a high bending stiffness and the grooves in the ribs provide good fastening locations for the rail. Base plates give extra weight to the sleeper. The disadvantage, on the other hand, is a relatively high price. The base plate with clip bolts is a classic indirect fastening. The base plate is fixed to the timber or concrete sleepers using coach screws. The rail is fixed by means of clip bolts, rigid sleeper clips, spring washers, and nuts. The clip bolt is inserted into the hole in the plate using a hammer lead. The pad between the rail and base plate is of masonite. This fastening derives its vertical elasticity from the pad and the spring washers. Sleeper life in combination with base plates can be dramatically extended by applying an iodide compound between base plate and sleeper. One piece of experience was that the sleeper life could be doubled to tripled through this measure. The introduction of the CWR track gave rise to the need for fastenings with greater elasticity. Certainly, in this case of concrete sleepers, which are susceptible to impacts, this is an absolute necessity. The clamp fastening system consists of a ribbed base plate fixed to the wooden sleeper by sleeper screws, clamp plates which fix the rail to the base plates by bolts with hexagonal nuts, where the flexibility of the fastened bolt is provided by used spring washers, which also helps to avoid the loosening of the nuts on the bolts under heavy vibration from rolling stock. Spring washers are applied also under sleeper screws. In some cases, a plastic rail pad goes between the bottom of the rail and the rail base plate in order to provide improved elasticity of the fastening unit. An advantage of the clamp fastening system is its strength of fixing the rail, which has a sort of anti-sliding benefit for the rail. Clamp fastening components like broken or damaged sleeper screws or bolts are easily to replace. The KPO fastening system is a typical clamp fastening system developed in 1926. The traditional rigid fastening, which so far has fulfilled its task to a certain extent, is no longer able to effectively meet the present challenge of heavy dynamic forces and therefore become loose under the impact of high-frequency vibration of the order of 800 to 1,000 cycles per second, even at a moderate speed of 100 kilometers per hour. In fact, this type of fastening is unable to hold the rail to the sleeper firmly for a satisfactory length of time because of the constant pressure exerted by moving loads. Due to the shocks and the vibrations caused by moving loads, the rigid fastenings become loose, and interplay between the components of the track develops, track parameters get affected, and rapid deterioration of the track begins. To solve these problems, a fastening which could safeguard track parameters and dampen the vibrations is required. This has led to the development of the elastic fastening. The problem with the direct spike fastenings with or without base plates is that the spike gets loosened during the traffic and need frequent hammering to kept in position, and that the rail foot and base plate cut into the sleeper, resulting in its faster degradation and loosening of the fixation. As the rail flexes downward under any rail load, it arches in a certain distance before and after the point of greatest upward deflection. Even if the amount of this blotch is very small, there are still 2 blows per wheel above, and this speeds up the loosening of nails or screws. To solve this problem, the development followed different ways. One of the ways leads to the nails or screws through the replacement of elastic spikes. The blows upwards and cut by the force of the bearing that is tightening more strongly. Should a permanent indentation of the rail foot in the sleeper occur, only slightly decrease of the downhold force of the elastic spike occurs. British Railways has been using elastic spikes, so-called T-spikes, similar to dog spikes, but with a curved head to have some inbuilt elasticity. Austrian Railway ÖBB introduced in 1930 an elastic double nail called Macbeth that had been used by ÖBB until 1955. Log spikes was developed by Germany to address the limitations to traditional methods like dog spikes and offer enhanced stability and durability to modern rail infrastructure. Log spikes go beyond the simplicity of the traditional spikes by incorporating mechanisms that securely anchor rails to sleepers or ties while minimizing the risk of rail movement, misalignment, and maintenance challenges. By introducing elastic spikes into the railway fastening system, the industry takes a significant step forward in ensuring a safer, more reliable, and efficient train operations. This technology showcases a commitment to improving track integrity, reducing maintenance demands, and accommodating the demands of the contemporary high-speed and heavy-load rail networks. Alright, in this lesson, we learned that fastening devices evolved from the initial spike fasteners to an improved rigid fasteners. Due to the limitation of the traditional spike fastener, it could also be further developed as an elastic-type spike to improve the performance fixing rails. Next time, we'll be learning how elastic-type structures are applied to fastening systems. See you!